Hey everyone, my name is Vinay. I'm a product manager at Snowflake.
And in this webinar, we'll be talking about how to use Snowflake ML capabilities, especially our distributed PyTorch on GPUs, to build deep learning models. So let's dive in. Today, we'll start with an introduction to what Snowflake Notebooks are. And specifically, we'll talk about Snowflake Notebooks that run over the Container Runtime, which is a purpose-built stack and set of services for ML and running ML at scale. We'll highlight a few key features and benefits for this runtime, and then we'll dive right into the use case that we're going to walk through. So we'll include a notebook. We look at how some of our other ML platform capabilities play a role, and we can see further what resources that will be helpful and beneficial for you to get started. So yeah, let's dive in. Great. So before we get into the notebook and the container runtime, I just wanted to put everything into context. So the Snowflake AI ML platform is a unified platform for all AI and ML. This includes generative AI, includes all the machine learning capabilities, includes the interfaces at the app level that can communicate and interact with these tools. And of course, you have all the infrastructure stack that includes access to GPUs and also the container runtime image that we'll talk about here. And all this sits on top of the Snowflake governance stack, which applies to both data and model governance. So in this case, the Snowflake ML box is the one that we'll be diving into. So great. So you're all familiar with notebooks. So notebooks are the common tool interface for data scientists and ML developers to build, research, and even take their ML models forward into production. Now, in Snowflake, we've introduced notebooks on container runtime, which run fully on a managed container environment where CPUs and GPUs are easily accessible. And of course, this is fully integrated with Snowflake, so you can load in any type of data, and is also integrated into downstream ML capabilities with automatic lineage capture, being able to register and deploy models, and so on. Now, the main benefit here is the fact that it's ML built, purpose built for ML. So it's flexible in the fact that you can bring in any package you like. It starts with a base set of ML packages, but you can easily extend it by pip installing any package, both in a private repository and a public repository. And of course, the infrastructure flexibility where you have the choice between the CPU and GPU pools. You have the granularity in choosing how many of these nodes in the pool that you'd like to use. The type of instances that are available in the pool can also be chosen based on the workload and so on. And it's very easy to get started, and we'll see in our demo how convenient the access to this runtime is when you use a notebook. Great. So kind of putting this back into the context of the ML box that we saw earlier. So the notebooks play kind of the glue, the cohesion across all these capabilities. So everything that you want to access that forms an AI ML platform feature is available through notebooks. Now, what we'll focus specifically here on is how these notebooks can be used to access the specific ML and modeling capabilities. And here we've got like access to open source, which you can see in the container runtime box right over here, with popular open source packages including PyTorch, LightGBM, XGBoost, and many more. And these are form the open source foundation for you to build your ML. But anytime you run into things like scaling challenges and you want to take advantage of Snowflake native capabilities, we have built-in APIs that take some of these popular open source packages, extend them with a minimal way to take advantage of our distributed compute, all in a very seamless fashion and fully integrated with the rest of the MLOps platform in Snowflake, including feature management through Feature Store, the ability to manage and serve these models through our registry, and now in public preview, also the ability to apply explainability and drift monitoring over and accuracy monitoring over these models. So again, in this demo, we'll focus on the notebooks, how we'd use some of our distributed APIs and specifically the PyTorch distributed APIs over GPUs to accelerate deep learning models. Great. So opening up the box even further, what is the container runtime? It is an integrated stack which begins with a base image that includes a lot of popular ML specific libraries. So one, because it's already installed for you, there is less overhead in attempting to address these conflicts and dependencies and all these challenges that you typically have with Python packages. And what's more, once you used open source and you want to take advantage of the scale, we have optimized and scalable APIs to be able to bring in data very efficiently, and also to be able to run training on a large scale across multiple cores and across the cores available in the compute pool for popular frameworks like XGBoost, like GPM and PyTorch. Now, all of this is facilitated with a Ray-powered compute cluster where we've optimized some of the already powerful capabilities that Ray offers for such workloads. And this runs in our Snowpark container services infrastructure, which is where we get access to these GPUs and CPUs. So what this means for you is you land in a notebook and everything that you see in the stack is easily available to you at your fingertips. Great. So in this particular session, we are going to dive into a computer vision use case. Now, many manufacturing companies, customers of ours, we've also seen applications in the market, often encounter challenges with things like quality control, quality evaluation, and it often could prove to be error prone when there's manual processes involved, or if there's a lack of clear documentation around what qualifies as a defect. So with computer vision models, we've seen that this becomes really, really simple, higher quality, higher productivity, and overall lowers operating costs. So it's a very important use case, and we and ML has already proven that it's capable at solving such challenges. But the more complex the use cases get, the larger the data sets become, the more fine-grained the labels in these data sets become. It just means that your compute needs to catch up, the algorithms need to catch up. So we're constantly seeing evolution in computer vision models. Now, the challenges that come with that is it becomes hard to scale this when your data sets become really large. And at the same time, the cost efficiency is a question that comes into play. Now, to do all of these things, of course, you do assume that there is infrastructure available for you and available to your data scientists and ML developers without having to be infrastructure experts or DevOps experts themselves. And all of this also translates to kind of the training infrastructure where you want to use the best packages available to you, cutting edge packages that are also automatically set up to take advantage of the scale out infrastructure. So all of these things are what we are going to solve for you, and we'll show you how we solve for it. So yeah, at a high level, it's a combination of optimized data loading and data processing, which we'll show via our data connector APIs. Easy access to GPU pools, so data scientists just have the best resource available at their fingertips. And how we've distributed PyTorch across multiple GPUs that significantly speeds up training times. So that way, there's a lot more iterations, a lot more improvements that you can apply without having to be concerned about cost or time. Now, great. So this is a quick start that is available for you to peruse while we go through this demo. So at any point in time, you can easily reference what's already documented in this quick start. There's links provided to you, and it's also included in here. And this is something that we can walk through. So just keeping in mind that this is the quick start that we're going to be using to also to look through the notebook. Great. So it's demo time. As I said, this is the quick start. It includes an overview section which talks about some of the same introduction that we provided to you. What is the environment? What are these capabilities in Snowflake that we're going to be using to run this demo? And we'll also get into some of the details around things like what you need to have it to get set up on your account, and then what you'll end up building. And of course, detailed guides for you to also have that data set handy and transformed in the way that you can dive into the notebook and just get started. Cool. So what in our demo today, we are going to be using the deep PCB dataset. It's a fairly large dataset with images and image pairs, basically, which is a combination of the printed circuit board image with defects in it and a file with a label for the type of defect and the bounding box for where the defect lies in the image. And we'll see in our demo how we transform these images to be able to work with PyTorch, and how we'd scale it out. Cool. So the first of the two files or the notebooks in the demo is about how we simply transform the data and set it up so it can be ingested into the notebook. So this is fairly simple. As we scroll down, so here you can see this particular data set has 8,000 samples. And what we'll be doing here is downloading. So the assumption that we have here, and there's more details in the quick start, is that the files, which includes, as we discussed, a data set, and which has base64 encoded image data, the defect class, and the bounding box. All these are saved into a Snowflake stage, and of course the details, as I said, are in the quick start. And so from the Snowflake stage, we'll talk about how that is just ingested for us to then work within the notebook. So it's fairly straightforward here. What we're basically doing is downloading these images from the stage. We are then combining the trained image. So the images that are downloaded transformed into base64 encoded images, and then that is being combined with their corresponding label file, and the label plus the bounding boxes are then with the base64 encoded representation are each logged into a table. So each table represents a combination of the image plus the type of defect associated with the image and the bounding box for that defect. Great. So here, the rest of this is just to demonstrate what that would look like. So if you run this, you can see an example of that bounding box, of that defect. Cool. So now let's actually go through and run this notebook. So in this example here, we are going to be using PyTorch as the framework to train the model. And the actual algorithm, the library for the image detection, image classification, will be an OpenCV library, a really popular library for image classification and image detection. So as you see in this notebook, it is using a lot of open source, and this is kind of where the flavor of the Container Runtime notebooks comes into play. It's open source first, but as we kind of navigate down the process, you'll see how we start to use more native capabilities, which speaks to the power of this runtime. So first is simple stuff, just importing common packages that we may need. Something to note is there's a lot of PyTorch included in here, and we've not explicitly pip installed it because it's all part of the base image. And let's actually go through and run this. Now, as we then look through it, so then we are also looking to import specific Torch Vision packages, and that adds to everything that we need. Now, one specific package that does not exist in the Container Runtime image is the OpenCV package. So we have to explicitly install this. And as you can see, it's as easy as a quick pip install. So once we have the packages installed, let's go and take a look at what infrastructure we're working with. So this is a notebook that is operating with 4 GPUs. So if I go and look at the notebook settings, this is running on a GPU pool with a GPU medium sized compute pool in AWS. So that comes with 4 A10s. And as you can see with what we're looking at, it's 4 A10s available for me to use. Cool. So again, like you recollect, this is the data set that we had. The full data set with all the defects rolled out comes up to about 120,000 samples. Of course, in this example, we're not going to walk through all 120,000 samples. We'll downsample it. So just going through some of this, you can see it's a fairly large data set, and we'll also see how what that data set looks like. Now, yes, as you can see, it's a 120K sized data set, and we'll pick just a fraction of the data set to explore a bit to see what we're dealing with before we dive into the details of the training process. As you can see here, this is a sample, and we'll show what we're working with. Great. So we have the class set up, the data set mapping class set up, and now we can actually go and see what the one of the images look like. So you can see here, this is an example of the labeled data set image. We have scanned image of a PCB, and it's identified that there is some sort of defect in this place. And we'll see later on in the notebook how when we apply inference, we'll sort of get back some of this. Cool. So now we have a good sense of what we're working with. We already have a encoded version of this data set that we can directly feed into our training process. So let's just get back to where we were. Now, the training portion is where we'll get into some of the meat of the container runtime, where it shines, where the data connector comes into play, where some of the distributed training comes into play. So what we have here is you start with a training function, and that's again typical open source, just modified to work with a distributed data parallel process. We'll use a sharded data connector, which is an API that the container runtime provides that optimizes for the distributed PyTorch. And then we'll see how the actual execution of this distribution takes place. Now, one thing to see here is what you're dealing with under the hood. So this notebook, yes, gives you all of the familiar Python interfaces, but know that it's running on a really large cluster with a fully managed cluster where it's abstracting away some of the complexities here. So in this case, what you can see here is you as a user are submitting requests, and what's happening inside the Snowflake SPCS compute pool is you have the notebook service that is communicating with the container runtime service, passing in these training requests or the data connection requests. And the container runtime service is the one that is mapping this into the corresponding GPUs to execute in, and would, of course, also reduce the results back and feed it back to the user. So under the hood, you have on a particular node in the compute pool, you have all these services running which are capable of mapping into the GPUs. And as you scale out to more and more nodes, you can imagine a similar architecture where other worker services that can be kicked off from the notebook would all take advantage of every node in the compute pool. So in this case, we have 4 GPUs. You would have this container runtime service that automatically leverages the 4 GPUs and passes in the training function to each of the GPU. So they're all working in parallel, trying to train different portions of the data set and combining those results and providing a model at the end of the day for you to take forward into production. Now let's look at what is happening specifically with the training function. So note that this is standard open source training function. This is something that you could easily pull in from any Kaggle project anywhere where people are using this popular public data set to train image classification and detection on. But as we look into it, you can see a few specific things for set up for distributed processing. Here is just basically setting up the context to fetch the appropriate rank in the group of the GPUs that exist. So if I have 4 GPUs, you want to get the right index that is that this function is currently operating under. And then a few other things to note. There's a particular protocol to communicate across GPUs for each of these processes that is optimized for GPUs. So the NACL protocol is something that is most commonly used. So these are only 2-3 things that you probably would need to include in this code. But the rest of this, as you can see in the comment here, is just typical open source PyTorch training code that happens to use the OpenCV model. It's fairly straightforward what happens in here. So this is basically just using abstraction to iterate through each of the data sets, transforming them into tensors. And then as you go into the actual training sequence, it's a standard optimizer followed by a forward and backward pass. And each loop in this particular shard of the data is simply going through the sequence and until you converge to a point. Great. So again, the takeaway from this is it's just standard open source code which you can find anywhere. You're more than happy to take what's here and go forward with it. Note that you're still saving whatever is a portion of this model to the local file system. And that would eventually be what you would also read back to use to register in the model registry. Cool. So we have the training function with a little bit of context provided so it knows that it's working in a distributed fashion. And then we look at how some of the specific optimized APIs that we've introduced play a role. Now, let's actually go back and execute this. Let's read into that. Okay, cool. So the next step is actually running the training. Now, this is likely to take a few minutes, so let's kick it off while we go and examine what's happening here. Now, let's take a look. So here, what's worth looking at is specifically this package. So the Snowflake ML modeling distributors package. So the distributors package is a new namespace that we've introduced which includes PyTorch, XGBoost, and LightGBM. And this is built to be as close to open source as possible. And you'll see in this example how this looks extremely familiar. Now, what we'll see here in PyTorch, in the PyTorch distributor, is how in combination with the sharded data connector, it's extremely optimized to work with GPUs. Now, the sharded data connector, as the name may imply, is effectively reading the data in shards, which is basically saying, let me distribute the data so I can read it in parallel. But then rather than combining it back and giving you a single monolithic data set, it is keeping the shards and with each shard mapped to, let's say, the number of cores I'm working with. So it's 4 GPUs. Let's say I'm working with 4 shards. So it keeps the shards the way they are, and it feeds each sharded data into this PyTorch training function that we saw above. So it's closely mapped to the actual training function. Because this is distributed data parallel, each training function is operating on a piece of the data set, and the sharded data connector is making sure that is operating efficiently. And we'll see in a bit what that looks like. So once I have a definition of the distributor setup, here you can see it's a simple scaling config I need to provide. And here I'm asking it to use four workers because there's 4 GPUs and so on. So great, it's actually finished. So we've taken about a minute and a half to run through 5,000 images, which is fairly impressive. And all of this was done in a really efficient manner, and I can show you in a minute how. So the materialization started by kicking this off. So note that until this point, no data has been loaded in, nothing has been executed. It's all just code that's built up to materialize it is one call. So if we quickly hop over to our slide deck real quick, we'll take a look at how some of those efficiencies play a role. So one, simply using the data connector gives you a significant speed up because it's Snowflake native data, so there is a lot of optimizations built in how we equally distribute the load, how we use the most optimal way of memory utilization, and a lot of other efficiencies that's been built in. The second thing to note is how we are optimizing the entire data plus processing flow to avoid things like GPU stalls, and this gives you best GPU efficiency. So as you can see here, with each shard of the data, you are avoiding reading the data first, having the GPUs just wait, and then passing the data into the GPUs for it to run the training. So what is happening here is because these data pipelines are split into 4 pipelines where you have 4 training processes. While you kick off one training process, the data has been loaded in the background. So as that process starts up, the data is already available in memory. So that way it's kind of pipelined in the fact that there is to ensure that the GPUs are best saturated. So let's get back here. So as you can see here, the benefits are clearly seen with speed up in the runtime. And few things to see here, maybe in the log, you can see that it's using 3 ranks indexed 0 to 3. So that shows that is using the 4 cores for training. Awesome. So that's actually taken us pretty far. We've read the data, we've loaded the data into memory, we've applied the training function, we have distributed training across GPUs. And in fact, it's taken us a minute and a half to train 5,000 models. Now, you would want to then scale this out, and we did run this on 100,000 images, which is much larger than what's even in this data set. And some of our benchmarks showed that this completes in about 30 minutes for the same configuration, which is hopefully is very impressive to you folks, because it's typically, for those who have experienced running this type of workload and on any other system, it could take significantly longer. Okay, now that we've trained the model, it's fairly straightforward to then take this model forward. We will register this model into the Snowflake model registry, which is a really straightforward log model call with a reference to the model and some metadata included. And once that's registered, it can be fetched, loaded back to be able to infer, or you can even start up a service, which would be a SPCS service. So the model is available for both batch transformations and online transformations. So in our case, what we do is we'll simply fetch the model back, and we've seen here that running this through one of our records in the data set, gives you this bounding box and also the appropriate defect that it's been able to infer. And what we've also done is really quickly display that image. And we can see here it's identified 4 defects for each of the type of pinhole defect with a very high confidence score, and appropriately pointed out where in the PCB that defect lies. Great. So yes, as I said, now that the model is ready, it's clearly shown that it can detect defects. You can set it up as an SPC service, and what you can also do is easily create a Streamlit app in just a few lines of code to be able to pass in one of these images or upload an image and run it through that SPC service to continuously show these defects and as the images are uploaded. All right, so that was our demo. Hope that was helpful. So we've got some resources that will provide you more information. Starting with our feature documentation, this will be our public docs and our Snowflake ML page where you can learn more about all of the products. And so feel free to run through that quick start as we've shown you here. And if there's any more information you need, don't hesitate to reach out through your account teams.
Thank you for listening. You can learn more about Snowflake's ML features and capabilities at snowflake.com/ml.